Okay, boys and girls, gentlemen, ladies, people, folks, here we go. We're going to talk about motion maps. Some of you have already seen a little bit about motion maps, and some of you haven't. So, we'll just start from the top. What we see here is a picture of some cars. That's right. Cars. You're writing this down, aren't you? You better draw this on your papers. Maybe not cars like this, because I know probably most of you can't draw anything quite this nice. But if you could just make some kind of sketch on your paper, maybe even just boxes. Some of you can probably handle boxes. So just draw some boxes here on the board, or rather your paper, that indicate that you have some cars. And you could even write the word cars in there somehow, some way. Maybe that's good enough. I don't know. I don't really care how you do that, as long as you know on your paper you have some cars. Now, for the motion map, we're going to do two things. Two things are mandatory for motion maps. First of all, you have to decide where is the zero position going to be. So I draw a line, and I put 0 under it. It's very complicated. Now, the other thing you have to do is indicate what direction is positive. And I'm going to say, for our purposes here, that the right, for me, is the positive direction. So I draw an arrow to the right, and I put a plus sign to indicate positive. So, again, two things necessary for a motion map. You indicate where the position is 0, with a vertical line typically, as you see here. Ooh, look at the laser pointer. 0 here, and you have to point in the direction that you're calling positive. I usually call the right positive because that's the positive direction on a number line, and I like number lines. So, back to the motion map. If you see the cars here, imagine that these pictures were taken in succession at 1 second intervals. It doesn't have to be 1 second, but let's just say. So at 1 second, or at time 0, let's say, the car is here. After 1 second, it is in this position. After another second, it's in this position. And after another second, it's in this position. So, how do we make that look in a motion map? Well, if this is my 0 position, and I'm going to say the car starts at the 0 position, then I will draw a dot. A dot represents the car position at a certain time. Because we know that the car is actually moving and it has some velocity, we draw an arrow, because velocity vectors are arrows. So we draw an arrow. This indicates a velocity in the positive direction for the car at this moment in time. Now, how about this moment in time? Is the car doing the same thing? Yes. So, we draw another arrow. Actually, we don't draw another dot at the next position, and we draw an arrow. Now, the question is, do we draw an arrow the same length as the first arrow? Hopefully you're saying yes, because the second arrow needs to be the same length as the first arrow to indicate that what has not changed about the car, its velocity has not changed. Therefore, the arrow stays the same length. Now, we have the car at this position. So what do? Another dot with another arrow to indicate it is still doing what it was doing before. And now another dot for the last position of the car with another arrow. And again, we see now that we have indicated with 4 separate moments in time that the car is doing the exact same thing, traveling with a constant velocity, same length arrows at every moment in time. There's your motion map. Let's move on to another one, shall we? We shall. These cars are moving faster. How do I know this? Because they're further apart than the last set of cars that you see here. This is what we worked on the last time. Here is what we have now. Oh goodness, how's this going to turn out? I don't know. Let's see. First of all, what two things do we do when we draw a motion map? Hopefully you're remembering. We indicate the zero position with a vertical line, writing the zero below it. We indicate which direction is positive, which will be, again, to the right, with an arrow and a plus sign. And again, I'll remind you that velocity vectors are very good at telling us what we need to know, which is two separate things. One, how fast, and two, what direction. You might be thinking to yourself, well, how do we know how fast something is? By looking at the velocity vector arrow. Well, how long the arrow is tells us how fast. What direction the arrow is pointing tells us what direction the travel is. Oh, this is fantastic. I hope you're following along. So, this first car right here, similarly to the way we did this the last time, this car is, let's just say, starting at the zero position, since that's where I've marked it, and we'll draw a dot, which indicates, again, that's where the car is, at time zero, we'll call it, and at position zero. Now, what's the arrow going to look like this time compared to the first time we did this? These cars versus these cars. Take a moment, possibly, and on your paper, draw the motion map that you think this should look like based on the difference now in how the cars look. Again, this means that they've had a further change in position in each time interval that you see here as compared to what they did before. So I wonder how their arrows will change. Oh, we shall find out. Okay, so hopefully you took a couple seconds there to, on your own papers, draw this out, how you think it might look. And so, the question is, how long is this arrow going to be? Well, I'm going to make it all the way over to here, because that is about where the next vehicle picture is, and where my next dot will go, and then another arrow about like what we saw on the first arrow, and then another dot to indicate that this is the next position of the vehicle, and there we have the last arrow. Now hopefully you're seeing that these arrows are longer than the arrows we had on the last set of cars. And why again would they be longer? Because it's going faster. What the? These cars don't look like they're doing the same thing as these cars or these cars. Oh, this tricky fella. So, here we go, people. These, oh, look at that, they move around. So, uh-oh. What are they? Oh, I don't know what's happening here. So, the two things that we always do first for a motion map, I hope you're finally getting this now, third time's a charm. You draw two things. One is you indicate the zero position. Now here's the question. On this set of cars here, and again, notice, this would be happening before this one, which happens before this one, so this is the end of this line of cars, since they're traveling apparently to the left, not to the right. So, where is the zero position? I don't know. I'll just keep it where I had it the whole other time here. I'll keep my zero position right here. Why? Because I can. So, I'll still say my positive direction is to the right. Why? Because I can. Didn't you catch it the first time? So, where is the car at the beginning of this scenario? It's way over here. Oh, that's where it appears first in this motion map. So, I draw my first dot. Wait, you do this on your own. Dang it. Look at the picture and look at what I've drawn already right here. And you write out this motion map the way you think it should look on your own papers. I'll give you a few minutes. All right. Hopefully you're done. Good grief, I gave you enough time. So, this, I would say, my first dot is going to be over here, which I already gave it away. First dot right here. First arrow, like that. Maybe straighter, whatever. Another dot is the next position of the car. And another arrow, which is about the same length as the first arrow. And another one for the third position of the car, and again, about the same position that it was before, or about the same length of arrow as it was before. So what do we see now? Where did this car start? Well, apparently this car started out here with a positive position. Notice the positive direction is to the right. So it started with a positive position, and it's traveling in what direction? Hopefully you're thinking the word I'm thinking, negative. So it's traveling in the negative direction toward the zero, or toward the origin, we could say. Now, folks, I'm making this up, okay? I can decide where my zero goes. I can put it anywhere I want. And because I had it here on the first one, and I had it here on the second one, I might as well put it here on the third one. Why? I hope you're getting the answer to this. Because I can. I think there's more. You hold on just a second. Holy cow, is this guy ever going to go away? So now we have a graph here. You've seen this graph before. It was on worksheet 1. We talked about it for 3 days probably. Good grief. So, what is this graph telling us? Well, this is the position we see. X in meters, the position. We have the time here. And we have cyclist A, if you remember correctly, here. We have cyclist B here. Now the question is, what is this going to look like as a motion map? Can we put 2 different objects on a motion map? Why not? Hey, we're making the rules. It's our motion map. So here's what we're going to do. I'm going to say that A is going to be red on this motion map, and that B is going to be blue on the motion map. So I have to determine where my zero position is going to be. Well, where's it going to be? I guess I'll just make it right here. Why? I hope you know the answer to that question. And so I indicate, again, where the zero is, and I indicate which direction is positive. And I want to the right to be positive, so that's what I make it. Now, if I want to draw A on this motion map, what do? Well, first I have to look at the graph, and I look at A's line. And I see what? Well, where was it at the beginning of this graph? At position 0. What was it doing? Well, now I look at the slope. And the slope is a positive slope that's constant. So what is that telling me? A constant positive slope. And hopefully by now you remember that the slope of a position time graph is what again? Velocity. So it's traveling in the positive direction with a constant positive velocity. What is that going to look like as a motion map? Well, A starts at the 0 position, so there's my dot to indicate the 0 position for A. Now, it's moving in the positive direction with a positive constant velocity. Now, how many dots do you put? I don't know. I'm making this up. Now, you could probably put as many as you want, really. Clearly, this thing goes beyond 5 seconds. So, for instance, if we were to say that each of these arrows was 5 seconds, this is going well past 5 seconds. So 1, 2, 3, 4, 5 seconds. We're just barely halfway into this graph here. That's fine, though. If maybe every one of these is worth 2 seconds. It's up to you. The person who draws the motion map makes these decisions. I'm putting a lot of power in your hands. So, isn't this even better than me being there? You can hear me, and yet you can't see me. I'm there, but I'm not. I'm sitting in my living room in my recliner right now. Isn't that odd? You're hearing me talk right now in that room while I am sitting in my recliner in the comfort of my own home. Oh, that's amazing. Oh, this technology is just amazing. Good grief. So, I don't even know where I was. Oh, yes, I'm talking about B now. Now, here's what I want you to do. I'm going to give you a minute here, and I want you to see if you can figure out how B is going to look on this motion map, judging by what we just talked about with A. And now B, since it's not the same line as A, it looks a little different. There are some things about it that might make B's motion map look different here on this little motion map, whatever you want to call it, thing. Yeah, that's a good word. So take a minute to do that. And we're back. So, what did you draw? I hope you drew something that looks like what I'm about to draw myself. So, first of all, you have to figure out, where's B going to start? Does B start at the 0 position? Well, look at your graph. Does B start at the 0 position? No, it starts with a positive position, away from the 0. In which direction? Yes, the positive direction. So, B's going to be out here somewhere maybe. I don't know. How far away? Whatever. You're making this up. Now, what are B's arrows going to look like? That's the next question. Well, the question is B traveling as fast as A? Well, the slope is not as steep. Is the slope constant? Yes. So the velocity is not changing of B, but is it as fast as A? No. So how do the length of the arrows compare? They should be shorter. How much shorter? I don't know. We're making this up. And so I draw some arrows of B that are shorter than the arrows of A. Are you getting this? I hope. And so this now indicates to us a couple different things. First of all, A starts at 0 and travels in a positive direction with a constant velocity. B does not start at the 0 position. It starts with a positive position ahead of 0 and travels in the positive direction with less velocity than A has. Oh, that's perfect. That tells us exactly what the graph tells us. Oh, man, we are almost done. I think there's one more. Oh, let's see what it says. And here's another one. Oh my gosh, is this guy ever going to quit? All right, here's what I want you to do. I want you to try this on your own. We have two different objects here, the two cyclists that we had the other day. And again, we have the same position time graph. A is doing what it's doing. B is doing what it's doing. So I want you to take a look at these graphs, and I want you to, on your paper, attempt to draw the motion map for these two graphs, and then I'll be back and show you what they look like. Oh, yes. And I'm back. So, hopefully, you figured this thing out. And I hope by now, the fifth example into this little mess, I hope you have figured out the two things you must include on every motion map. And again, it is a starting position of 0 and an indication of which direction is positive on your motion map. And again, we'll say that A is red and that B is blue, just like we did on the last one. And I'll try to do this quick enough because this is taking way too long. There's so much time that's gone by. It's just amazing. So, A starts at the 0 position just like it did the last time. If you remember when we talked about the assignment, we said that A is experiencing the exact same kind of motion it was in this graph as it was in the last graph. So, it starts at the 0 position. And it travels in what direction? Yes, the positive direction with a constant velocity. So your arrows, again, are pointing in the positive direction, and they should be as close to the same length as you can make them. And again, I'm drawing on a white, or actually on an iPad, and whatever. It is what it is. Deal with it. So, that's A. Now the question is, what's B going to look like? Well, B starts in a positive position, just like the last one did, only what kind of slope is this? You see this is a, what kind? Negative slope. So this is a negative slope, therefore, what direction is B traveling? In the negative direction. Oh. So it starts with a positive position out here somewhere, a larger positive position than it was last time, maybe here. I don't know. Is that too far? I don't know. We're making this up. So that's where it starts. Positive position, negative velocity, meaning it's coming back this way toward the zero or toward the origin. Now, the question is, how do the length of the arrows B here compare to the length of arrows A here? Hopefully you drew them smaller because B is not traveling nearly as quick as A is. So those arrows should be smaller and traveling in the opposite direction. Now here's the question. Should I keep drawing these arrows all the way over until it gets to the zero again? Well, I don't know. What does our graph show? Does B ever get back to the origin? No. B would have to be traveling for quite some time at that steepness right there to get all the way back down to about where the zero position would be. So, no. B does not get all the way back to the zero position, and so hopefully you didn't draw your arrows all the way back to the zero position because that would not show up on the graph. Oh, hasn't this been a pleasant day? You have an assignment, I believe, that will be handed out at this point, and I want you to do a couple things here. Let's see here. Hold on, I got to write some things down. Hold your horses. Good grief. So, what I want you to do is answer number 1, of course. Now, for number 2, numbers 2 through 4, I want you to do 2 things. With those descriptions, I want you to draw an XT graph, a position time graph, and I want you to draw a motion map. So I want you to draw, again, a position time graph and a motion map in the space provided under where the description of motion is. Do not do the VT graphs that are off to the side, the right side in the margin. Do not try to fill out the VT graph unless I guess you're feeling really confident about it, by all means. But I at least want you to, using the descriptions of motion on 2, 3, and 4, I want you to sketch what you think the XT graph would look like for that motion and what the motion map of that motion would look like. There's your assignment. Do not do the backside either. Look at this. I'm telling you all these things not to do. You better listen. Have a great day. I'll be back tomorrow if you're lucky.